Hello and welcome to the next unit, Dynamics of Circular Motion in Phys 1101. And this is going to be quite a short unit because all we're doing is taking a whole lot of ideas that we've been developing over the last few units and we're putting them together and applying them to one special case, which is uniform circular motion. So in this lecture, we're sort of stepping back from dynamics back into kinematics for a moment just to get some extra bits of kinematics that are particularly useful when you're talking about motion in a circle. So here are some things that you saw way back in the last lecture of Unit 4. And if you're in my course, that's about 2 weeks ago for you at least, so it's worth reviewing. So in uniform circular motion, we've seen from just doing delta v, right, vector subtraction, that the acceleration for uniform circular motion points directly to the center of the circle. And remember, that's not true if the speed is changing. If the speed is changing, then the acceleration vector will be directed more forward or more back, right? Forward if it's speeding up, back if it's slowing down. But if the speed is constant as something goes around a circle, the acceleration points straight in. And then since the velocity vector is tangent to the path that the thing is following, that means that the velocity and the acceleration are always perpendicular. And we saw that the magnitude of the acceleration vector is a constant, and it turns out to be v squared over r, where v here is the speed. So these are all things that we'll need to keep in mind throughout this unit, and the main point of this unit is that we're connecting this, especially the v squared over r part, with what we've just seen in the last 2 units, which is that the acceleration of an object is the net force on that object divided by the object's mass. Now, we're not going to really get to that in this lecture. In this lecture, we're going to extend some of these kinematic ideas we saw before, just to give ourselves a few more ways of measuring things before in lecture 2 we move on to using this to draw conclusions about forces acting on things that are moving in a circle. Let's think about this very simple question. How fast is this merry-go-round turning? And that seems like a simple question, and really it is, but this question turns out to be a little vague. And we can't be vague when we're doing physics. We need very precise definitions. So there turn out to be several ways to answer this question, and some of these ways are equivalent, as we'll see. So we need to think about what information you need to be able to answer this question in a precise manner. Or in other words, what is it that you measure? And then a question that seems like it's the same question perhaps, but it isn't quite the same question, is how fast is this child moving when the merry-go-round is turning? Now that's closely related to this question of how fast the merry-go-round is turning, but it's actually asking about a slightly different quantity that you can measure. When we're talking about things turning, there are 2 closely related terms. Rotation is each turn of a rotating object. So this merry-go-round is rotating. Each time it goes once around, you call that a rotation. On the other hand, each time this child goes around the circle, that is called a revolution. Now, notice here that the revolutions of this child take place in exactly the same amount of time as the rotations of the merry-go-round. And so often these 2 things are so closely related that people mix up the terms. Even physicists, we get a little sloppy about our use of these terms. Just be aware that there are 2 terms. And returning to this question of how fast the merry-go-round is turning and how we answer it, in this case, it's equivalent to the question, how fast are the children revolving? Or in slightly more everyday language, how fast are the children going around the circle? Now, that is a vague question. So 2 slightly more specific questions we could ask are, how long does one revolution take, right? How much time does it take for a child to go once around the circle? Or, how many revolutions take place in a given time? Say, a minute. How many revolutions take place in a minute? I'm going to time this merry-go-round, to find how long one revolution of the children takes. So I'm going to watch this kid in the striped shirt to determine this. And the obvious thing to do is to time one revolution. But that's not very accurate because of human reaction time. Human reaction time can be up to about half a second. And so what you want to do is time multiple revolutions so that your reaction time ends up being a small fraction of the total. So I'm going to count 5 revolutions, and I'm going to count each time the kid in the striped shirt passes the front here. So here I go. I'll let it go around once before I start. 0, 1, 2, 3, 4, 5. So according to the stopwatch, the time for 5 revolutions was 12.435 seconds, and it's worth stopping just to talk about significant figures for a moment. Remember that my reaction time is perhaps as much as half a second. So I would expect if I redid this timing, this 4 here would change from measurement to measurement. And that means that this 3.5 is certainly garbage. These are not significant figures. So I will say that my delta t for 5 revolutions is 12.4 seconds. And now, clearly, for 1 revolution, it must just be a fifth of that. My time for 1 revolution is just 12.4 seconds over 5, which my calculator informs me is 2.48 seconds, where again, that 8 probably has some significant uncertainty associated with it. So that's one way to answer this question, how fast are the children going around the circle? You say how long one revolution takes. And we have a word for that. That's called the period of the revolutions. But we can also, of course, ask how many revolutions take place in a given time. And we call that the frequency. So we found that the time for 1 revolution was 2.48 seconds, and that is what we call the period. Now let's find the frequency. Remember that the frequency is just how many revolutions there are per unit time. So what we know here is that there were 5 revolutions in 12.4 seconds. And if you punch that into your calculator, you'll find that's 0.403, and look at the units, revolutions per second. And that makes sense, a little less than half a revolution every second. That makes sense if each revolution takes a little over 2 seconds. So this is the thing that we call the frequency. But now notice something. The period, which we'll call capital T, and the frequency, which we're calling f, and look at how they were calculated. That period was 12.4 seconds over over 5, right? So this was the time for the 5 revolutions divided by the number of revolutions. Well, the frequency, if you look at it, we did 5 revolutions over 12.4 seconds. And so we took the number of revolutions divided by the time that they took. Hey, look! Those are just the flip of one another. And so we can just see that they always must be related this way, that the frequency is just the period turned on its head, 1 over the period. So we have these common sense quantities for describing revolutions, the time to go once around that we call the period, the number of times you go around per time that we call the frequency, and we've seen that the frequency is just 1 over the period. And the thing I want to stress is that this isn't a formula to remember. This is simply common sense. If you understand what frequency means, you know how to calculate it. And if you know how period is defined, then you know how to calculate it. And if you know how to calculate them both, you can just see that this relation is correct. It's worth taking a moment to think about units. This came out 0.403 revolutions per second, right? Literally 0.4 revolutions per second would mean the child goes about 2/5 of the way around the circle each second. And a revolution per second is defined as a hertz. Really, a hertz is a repeated thing per second. So in circular motion, the thing that's being repeated is trips around the circle. And because a revolution isn't a unit, it's a thing you count, that'll often be written as just 1 over s, 1 over seconds, or seconds to the -1. Now, you're probably more familiar with RPM, which are actually really inconvenient units, right? But a physicist would write this as revolution per minute. That's what RPM stands for, and writing it this way makes it clearer that there's a numerator and a denominator. And so now you can see that usually you convert out of RPM because they're horrible units to work with, but if for some reason you wanted to put this frequency into RPM, you would just do the usual conversion fraction, where all we're doing is replacing our seconds with minutes. And if you wish, you could now carry out that multiplication. We started with this question, how fast are the children going around the circle? And we found two ways to express how often they make a complete trip. But of course, we've just spent a whole bunch of this course on things like speed as ways of measuring how fast. And so let's look at the speed of these children. Well, a speed, we know their velocity is changing constantly, but their speed isn't. And it's a distance covered per time taken. Well, that we know, although we'll have to work a little bit. The time taken, well, we could say we know the amount of time it takes them to go around the circle once. That's the period. How far have they gone in that time? Well, they've gone the circumference of the circle. So that's 2 pi times the radius. I don't know what the radius of that merry-go-round was, but it's got to be around a meter, so let's go with that. So we can now estimate the speed of these children. It's just 2 pi times 1 meter over the period, which we found to be 2.48 seconds. And my calculator tells me that that is 2.53 meters per second. And notice that that is how the units work out, right? I have meters up here and I have seconds down here. So this is always something that holds true. The speed, v, no vector symbol, this is a speed, not a velocity, in uniform circular motion is 2 pi r over t. And that again is nothing more than the definition of speed, the distance covered, the distance around the circle is its circumference divided by the time taken. That's what we call the period. I just want to summarize and at the same time point out a few things about these relationships. So the period and the frequency, we just have nice simple definitions, and they turn out to be the inverse of each other, and that means you can flip that equation around like so. And the real thing to notice about this is that these are just two different ways of saying the same thing. So if you know the period, you know the frequency, and vice versa. The speed we can determine from the period if we also know the radius, and this is just the usual distance over time taken. And again, you can replace the 1 over t with an f to express it this way. But the real thing to realize about this is that if you know any two of speed and radius and either period or frequency, because they're really the same piece of information, then you can always find the third.